Okay, um, so for this video, we're going to explore infinity, particularly different sizes of infinity, particularly involving the number systems. So we'll just write infinity. Okay, so start with the basics. So finite, you can you can count it out and stop at some point, right? 3, right? Finite. Infinite, you just keep on going. Okay, seems fine. You might think, okay, just keep on going. It's the only size of infinity. And for a while, it'll look like we only got one size of infinity. So what we're going to try to do here is, just like we know that 3 is the same size as 3, because we can match them, we will do the same thing with infinity. So first size of infinity is this. This is the natural numbers. We count, counting infinity. All right. What's our next number systems? That's minus 3, minus 2, minus 1, 0, 1, 2, 3. All right, so this is the integers. Twice as many. All right, so are there twice as many integers as natural numbers? Well, clearly the natural numbers map into the integers, right? So that would seem to say, well, the integers are twice as big. But are they? Let me rewrite this. So we've got 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. Oh, I just listed them. So this is, so if we were to think of mapping it to the natural numbers, right, we've just listed them. Same size. Okay then. So yeah, we had that. We could even do something wackier. We could say, we could do, give me an integer, and if it's positive, let's say positive n, then we map that to 2 to the n. And if it's negative n, then we map that to 3 to the n. And so, and 0 just gets mapped to 0. Or say 1. But it doesn't matter. So this would generate the list, basically. So if I were going from here, that would be, sorry, 1, 2, 3, 4, 9, 8, 27, right? And so not only are the integers the same size as the natural numbers, but they seem to be even smaller. Or at least you could put them in a smaller version, right? You don't even need all the natural numbers, just a small set. And so basically, if you map a set into another one and map that set into the other one, you see that they're the same size. So if you can, we've got two sets map into unique targets into B, and then also map into unique targets. Then same size. Cool. Alrighty then. So the integers and the natural numbers are the same size. Cool. What's next? Rational numbers. We'll just go with the positive rationals, because the negative rationals and the positive rationals, you can line them up in that same fashion, right? Anyway, we could modify our things for the negatives too. It's fine. So we'll just do positive rationals. And the idea here, it's a clever idea, is we write the rationals out in this table. We have like 1, 2 over 1, 3 over 1. So these are just those numbers. Like that. And then you have 1/2, 1/3, 1/4. And then you have 2 over 2, which is just 1. You have 3 over 2. You have 2 over 3. 3 over 3. Right? And just fill it out. Alright, so now I've got this table of rational numbers. And they're all there. And just to kind of have in your mind just how much larger the rational numbers are than the natural numbers in terms of an intuitive sense, think about just between 0 and 1, right? You've got 1/2 in the middle here. You've got 1/4, 3/4, and you've got a 1/3, and you've got a 1/5, and you basically have 1 over n, all natural numbers. And then you can have like 2 over n for all n greater than 2, also between 0 and 1. Right? So you have almost like, well, yeah, you have an infinite number of copies of the natural numbers just between the numbers 0 and 1. That's how big the rational numbers are, right? That's a lot. Just between those two. And then you have infinitely many copies of those intervals going forever, right? That sounds like a lot. So maybe we finally found something larger than the natural numbers. No. You may want to think about it a little. What I'm about to show you, you can only kind of see once in your lifetime. So, or come up with on your own once in your lifetime. So think about this table, pause, and come back in a couple of days. What we want to do is make a list of the rational numbers, right? That's what we want to do. What's the first one? What's the first one? What's the second one? What's the third one, right? We need to be able to answer that question in terms of some process. So I made a table here. If you wanted to write down a list of the rational numbers, how would you do that? Say using that table. I'll give you a moment. Pause. 2 days later, welcome back. You're now ready to see my solution. You could have had another solution. There are many ways of doing this, but here's the classic way. I'm going to go, well, I'll go with green. So start with here, number 1. It's a good place to start. First number is 1. Then we go over to 2. Now, if you keep on going, right, you never end. You never get to the next level. so don't do that. Instead, we go down, then we go over, and then we go down, we go over, go over, go over, go over, go over, right? And we're just gonna snake along all the numbers. And so we have a path that's going to hit every single number. If you give me a rational number, you know, I can do this table out until I get to it, right? If I just went along the top row, I would never get to the other numbers. But by circling around, we get to see every single number. So that's the list. That's the list. Same size as the natural numbers. So even though there are infinitely many copies of the natural numbers in terms of the rational numbers between 0 and 1, nevertheless, we can map them to the natural numbers. Now, when doing this list, you'll have repeats, right? Like, so you had 1 at 1, and then at 2 over 2 is just 1. And so you can skip that. If we didn't equate the numbers, you know, have that equivalence relation of reducing common factors or whatever, then they'd all be distinct, and that'd be fine too. It's not the rational numbers. Then, you know, you're trying to make a list, right? And so if you hit repeats, hit many repeats, just ignore them. All right. So far our hunt for the bigger size infinity is going too well. And here's another way of doing it. So our another way doesn't involve a table at all. So you give me a divided by b. I map that into 2 to the a, 3 to the b. So this encodes the rational numbers in terms of just these two products. Give me a number, and let's see, I'll just make it clear that this is in reduced form. So, for example, 5/3 gets mapped, sorry, let me not do the 3 there. 5/7 gets mapped into 2 to the 5th, 3 to the 7th, right? Which is whatever it is. It's a big number. Who cares? I don't care. They're going to be natural numbers here, so you can use them as powers, and that's that. And so these are all, so this list is contained in the natural numbers. So not only are the rationals the same size as the natural numbers, but you can even view them as being smaller than the natural numbers. You can encode them all into this very small subset of the natural numbers. Just products of 2s and 3s. That's it. That's all you need. 5, 7s, 11s, whatever. You don't need them to encode this, right? That's like, wow. Again, like really think about, you know, the intuitive sense of what rational numbers are in relation to natural numbers. So many more, and yet by the power of infinity, they're all the same. So maybe this concept of being able to list things out as sort of natural sense of size of infinity is a bad concept, right? If it doesn't give you anything different ever, then it's a stupid concept. It's not useful. Your pessimism is a little premature. Let's go on to the real numbers. So, real numbers. Now this is a cool argument. All right, so try to think of listing out the real numbers. Now, in some sense, so real numbers are just anything of the form 3.1415, like that, right? Or just 7.8917359268. Goes on, right? Whatever pattern, or no pattern, whatever infinite string of digits. String of digits. All right. And for the sake of starting small, let's just consider the reals between 0 and 1. All right. So that's more modest goal. Just try to list them, right? Let's try to list them all. So before with the rational numbers, we had this nice sort of A over B, right? And you could make that table. You could do that prime thing. There's something to work with. What do we have to work with here? What kind of regularity can we do? Well, I guess you could try. So we're just going to do from 0 and 1. And then, so do say 0 0.1, 0 0.2, 0 0.3, 0 0.9. Okay, so that'll be 1, 2, 3. Then we get to 10. We do 0 0.1. I guess 1, 0 0.1, 2, 0 0.13, 0 0.19, and then 0 0.21, right? 0 0.99. All right, so far so good. Counted a lot of numbers. Will this continue to work? Well, 0. Oh, oops, also forgot 0, 1. There we go, that's what we need. 0 and 9, right? And so then you have all the ones that go from first digit, 0, and then these other things. And then, what do we get? We get 0. Well, so this should have been here, I guess. So 0 0.001, 0 0.002, oops, sorry, 9, 0 0.00, 1, 0 0.101, right? You just keep on doing that. Seems good. So you get all the ones that terminate after 1 digit, all the ones that terminate after 2 digits, 3 digits, 4 digits. Just keep on going, right? Just keep on going. Seems good, right? Any particular number you give me, I will reach, a point at which I will have gotten the first whatever number of digits of that number, right? Well, basically what we've just done is this lists out all rationals of the form n over 10 to some power. So the tenths, the hundredths, the thousandths, the 10,000ths, blah, 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 blah. So not even all the rationals, which we know we can even list. Now that seemed like a pretty, I was sweating here that I was going to not find out what was going to go wrong here, because it's supposed to go wrong. And that's why, because like these numbers, these real numbers, you got to list an infinite number of digits before you know what you're talking about, right? Now the rational numbers, they have that repeating pattern. So like 1/3 is 0.33333333333. Now we didn't capture that on this list, but you could, because we had the ability to make a list of these things, because it's a rational number. But they're like that, right? So at some point you've got enough information for a rational number to say, I'm done with that. And so you could probably modify this list to include, things that have patterns. So like here, you could also do 0.1 repeating, 0.2 repeating, right? And then over here you could do 0.1 1 repeating, 0.12 with 2 bar repeating, or 0.12 bar with that repeating, and so forth. As you do all that, it gets much longer and longer and complicated, but it seems doable. So you could include all the rational numbers, as we know we can, because we listed them already. But that still doesn't get the numbers that don't have that kind of nice repeating patterns, the irrational numbers. What about irrationals? So these are like the square root of 2. Right, just probably demonstrated that can't be a rational number. That's for another video. So, we failed. Now, was that because we were dumb and just didn't find the right way to count them? So when mathematicians come up against something that they can't figure out, they throw a tantrum, basically. They say, fine, game over. You win. Basically, it's going to be a proof by contradiction. And before you continue, this is another one of those things where it's like kind of neat if you can come up with it yourself. So if you haven't already pause, and think about, first try to come up with a list yourself, right? You will fail. If you don't fail, then you've done it wrong. Just telling you. I know this. You cannot make a list of all the real numbers. So if you do come up with a list, figure out what's wrong with it. That's extremely useful. Figure out what you're missing. Then when you've given up on the idea of having a list, you say, I've got a list. Assume you have a list. Assume we have a list of all the real numbers. Find a problem with it. All right, so that's what the mathematician does, right? It's like, I can't do this, so I'm just going to assume I've got this, and I'm gonna find out what's wrong with it. So this is a good time to pause. Write down your imaginary list and think about what's wrong. Okay, so let's say we had a list. say, what? Lots of numbers. I don't know what they are. Don't care. So I've got a list. I have a list of some real numbers. And what can go wrong? Well, what can go wrong is that there's some number that's not on that list. Find a number not on the list. Number not on the list. And basically, think about it. If you're given these numbers, what's a number that's not on that list? Well, let me try to write it down. I'll write one down too. There's lots of numbers you could write down in this moment, right? But think of an infinite list, right? All right, so you don't want the number to be the first item on the list. So you look at the first item on the list and you say, well, that starts with 0.1. So you write down 0.2. So now it's not the first number on the list because it doesn't agree with that. I don't want it to be the second number on the list. I've already chosen the first number. So let's say that this was actually a 2, right? That's not looking good. And so the second digit is, say, a 9. So now that can't be the second number, right? See where I'm going with this? Changing, looking at each number on the list, and I'm writing down a number that doesn't correspond to any item on the list. And let's just, as I build up this list, I'm going to be mean to myself. So 2.99, so there's a 9 there. So instead I will go to a 0. So now that doesn't agree with that number. And if I were to do get 299.5 here, well, then I write down a 6. And I just keep on going. So look at nth item on list and add 1 to the digit. And that is the nth digit. Now, there are many, many numbers not on this list, right? I can change any of those digits. 2, 3, 4, 5, 6. But for the first digit, any of those would have worked. Anything except for 1. And of course, I could just make sure it varies from every other digit, right? I could have just, whatever for the first one and then change. Like, there's so many ways to write down a different number. So many ways. But basically, the simplest thing is change these. That's the basic idea. This number is not on the list. Okay, cool. And so the real numbers are bigger than the natural numbers. They are a different size of infinity. They are much larger than the natural numbers. So large. Fast numbers system. There's no question. Now, so you have all these different numbers on this list, and then basically what happens? Well, you have to ask yourself, how does this go wrong for the rational numbers, right? Because the rational numbers, like these could be rational numbers, right? These could have been 1, 2, 3, 5, 8, right? Just, or whatever. It can be repeating. This list could have been all sorts of rational numbers, right? And I've just constructed another number that's not on there. So what's the deal? Well, no reason to believe that this is a rational number, that this construction makes a rational number. And so it is a real number. It is real, but may not be rational. Right? No reason to believe it is. There's no way to know it is until you write down the whole thing. Even if it repeats, you happen to write a list that basically repeats, you don't know until you've gone through all infinite number of numbers on there. So that's that. So that's why the rational numbers don't fall into this argument, because even though you can still construct a number from whatever list of the rational numbers you've made, that number is not necessarily rational, and presumably won't be. Particularly if you've actually listed out the rational numbers, it will definitely not be a rational number because you've got that list. We know we can make that list. It's a made list. And so this constructs a number which is not rational from that list of rational numbers. It is a real number. You have a method of constructing it. Given an actual list of real numbers, you definitely have a process for writing down this number. It exists. It's a decimal thing. You can get an approximation of it as many digits out as you want, right? But you don't really know what that number is precisely because you need to go through infinitely many stuff. So infinity is weird like that. All right, good. Yeah. So those are the same. So those are the notions of infinity. The complex numbers are actually the same size as the real numbers if you're using the real numbers. So you can actually make complex integers if you like, and then they'll be the same size as the natural numbers, or complex rationals, same size as the natural numbers. That's sort of that extra dimensionality. It doesn't change the sizes of infinity. It's essentially kind of a generalization of the rational argument. It's a little bit more complicated to talk about, but basically anytime you just take a set and pairs of things from a set, or any number of things from a set, give a number, they will, it'll be the same size. There is, so this is probably a good time to stop, just saying. The next bit is a little bit more advanced, but I wanted to show just, well, are the square roots and stuff responsible for this largeness? Responsible for the largeness? So we included a whole bunch of things to solve power problems, right? So square root of 17, cube root of 91, fifth root of 5, whatever, right? It's a lot of numbers. And then all their combinations and everything. And all those things are irrational numbers. They're not rational. Again, it's a separate video. But basically, I want to say that no, they're not responsible. They're actually same size as the rational numbers. And the argument is kind of cool. Involves sort of polynomial stuff, so maybe come back to this portion when you've got polynomials under your belt. But essentially, all these things are roots of polynomials. They are all roots of polynomials. And so polynomial might be something like, I'll just use a here, right? And say a5 x to the fifth plus a4 x to the fourth plus a3 x to the 3 plus a0. And that's kind of like a polynomial. And you can keep doing that with an x to the n. So you've got all this sort of numbers here. And then you also have, and there are n roots for n degree polynomial. Okay, and these are the solutions. So square roots, cube roots, so forth, right? That's all covered by these things. And all their weird combinations, you can make polynomials out of them. These are called the algebraic numbers. And I felt like we were completing the real numbers to include these, right? I originally talked about the real numbers in order to include the square root too. Fine, good. Well, these are same size as the natural numbers. Now, there are a number of arguments for this, but one of the reasons I did the power thing is because that's a nice way of actually seeing this. So these are, we'll just roots, maybe, rational, could be rational roots or natural numbers, coefficients could be, but you can always clear out the denominator with these rational coefficients because you're setting it equal to 0. So multiply by whatever you need to, and the 0 doesn't change it. So these are all, assume all natural numbers. You don't have to do that for this argument either. You could you can just always add in primes. There's infinitely many primes, by the way. That's important for this. So basically we encode the roots like so. 2 to the say root number. So think of ordering the roots by some process. This is the first root, second root, third root, so forth. You can do that. And then you have 3 to the a0, 5 to the a1, 7a squared. So 5 to the a1, 7 to the a2, 11 to the a3, 13 to the a4, 17 to the a5, and so on, right? Now, any given polynomial with a finite number of coefficients will stop. And we can read off what those coefficients are from prime power decomposition here. We just have a product of primes. We look at the powers of each prime. We write down that number. So, for example, 7x cubed plus 2x would be encoded as, so we'd have 1, 2, or 3 here, which root? And then we'd have 5 squared and 7, x cubed is 11 cubed, right? So 5 squared times 11 cubed, and then times either 2, 4, or 8 would tell me which root I'm talking about. And so I can completely encode every single solution of the integer coefficient polynomials with this process. So they're all contained in the natural numbers. Mind blowing, right? Like, that's a lot of numbers. And they're still the same size as the natural numbers. But even more, think about this. What are the real numbers you know? Well, you got the rationals and the natural numbers. Well, natural numbers, rationals. You've got the roots and stuff. There's pi. Maybe you can do stuff with pi. There's a number called e, which you might not know about yet, but will soon. And that's kind of it. So basically almost every number we know is an insignificant portion of the real numbers. So that's weird, right? It's important to kind of think about where we are at this point. We have constructed numbers that serve a purpose for us. We completed the real numbers in order to be able to say we've got square roots and all these things. We did it in a way that was very inclusive and included a lot more stuff. And these things do get used. They are part of functions that, come out of things that we're going to see. But yeah, they're really big and they have some very strange properties. But so it goes. So yeah, take that for what it's worth. Infinity can have different sizes. There's a whole hierarchy of infinities. One of the interesting things is, so there was the natural numbers. That's the smallest size of infinity. I'll just tell you right now. That's, if you're going to be infinite, you're either that size or larger. Then you've got the real numbers. We don't actually know about whether the real numbers are the next size of infinity or way out there. There's some things that they can't be, but basically they're huge, and we don't actually know how huge. There's a whole bunch of other kinds of things of infinity that can be in there. It kind of depends on the axioms one wants to use. There's lots of weird things that happen if you make the reals the next size up, although there's some really nice things that happen with that too. And so that's kind of the weird world that mathematicians exist in. For people living in the real world, none of this is all that concerning. Anything you write down in approximate form, that's a rational number. You got to stop, right? It's zeros afterwards. Or maybe you've found a pattern and you indicate that. But other than that, it's all rational. And there's even kind of a finite limit. So the size of infinity stuff, it's a mathematical curiosity. It's pretty cool. Is it actually real? It's a question that doesn't make a lot of sense to me. It is and it isn't, right? We cannot produce it in our reality, but but assuming that it exists and working with it makes things so much easier and understandable that it kind of seems like it should exist. But that's the kind of things to wrestle with. Math is a tool first and foremost, and if the constructions you've made in order to make the tools work well, as long as they're working well in reality, it doesn't matter kind of the weirdness on the back end. Let the back end worry about it. The front end is what matters. Does it give you the tools? So it's like the complex numbers. They allow you to sort of say, oh, I got these roots, and so now I can factor this thing. There's some mysterious stuff going on there, but it's fine. And it's just like use what you need to use, and you can ponder weirdness, infinities. Infinity is really cool. But and some things are known, some things are not known. It's fun. I hope you enjoyed this. Does it really impact anything? No. I'll tell you right there. This is totally a bonus kind of thing. It's something that's really neat, and some people dedicate their whole lives to studying this. I think we call them logicians. I was almost tempted into that field when I was a younger person, but I resisted. But I still love it. Anyway, so that's the sizes of infinity.